Hey folks, welcome back. Mr. G here. Welcome back to the next in the series of lectures for electric machines, ELIC 200. Today's topics, we're going to talk about conductors, insulators, and overcurrent and protection type devices. So, what makes a conductor a conductor? What makes an insulator an insulator? Some of the properties of it, something that has to do with the transmission of electricity from one place to another, and then looking at protection devices. So let's get started. If you remember from your basic electronics classes first semester, what makes a conductor and what makes an insulator actually comes down to the atomic structure of whatever material it is. A conductor, what makes a conductor is fewer electrons in the outermost shell of any atom. So the outermost shell is called the valence shell. So these are valence electrons. So few valence electrons or what you're going to find in a conductor. An insulator has typically 8 electrons in the outermost shell of the atom, making it an insulator material. So the idea is if we applied energy, some energy to these two types of atoms, this energy is going to be absorbed by the valence shell electrons. This energy would cause this one electron to easily leave and enter the conduction band and therefore flow freely. The same amount of energy would be divided up amongst all of these 8 electrons in the outermost shell. And each one individually would not get enough energy to actually leave and enter the conduction band. So I like to describe it like this. A conductor is a material that conducts electricity under normal conditions. An insulator is a material that does not conduct electricity under normal circumstances or normal conditions. And I say the normal part because if you were to apply enough energy, so if you take a piece of wood like this desk for example, if you apply enough energy, you can actually get the wood in the desk, to conduct electricity. Typical example, a bolt of lightning hitting a tree. So the bolt of lightning carries enough energy that you can actually force electricity through something that is normally an insulator. So a conductor is something that normally conducts. An insulator is something that normally does not conduct, but you can force an insulative material to conduct electricity if you apply enough energy to it. So that's the difference between a conductor and an insulator. So what we're going to do is we're going to look at properties of round copper conductors. So there's something that is referred to as the American Wire Gauge Chart, AWG. American Wire Gauge Chart is a gauge, if you will, a specification that round copper conductors, there's also one for braided conductors and things like that. If you're looking for the properties, the physical size, how much does it weigh, all of those things, then you would go to one of these tables and look it up. So as you can see, down the left-hand column on the table is what's known as American wire gauge number. The gauges vary. The larger the number, the smaller the wire. The smaller the number, the larger the wire. If we take an example of the wires that we use to build our little circuits with our breadboard, they're typically a 22 to 24 gauge wire. They have certain size specifications. So you can look at the diameter of the bare conductor. Since we are working with the metric system, we'll look at it in millimeters. You can also get the cross-sectional area of such a conductor. And then the resistance of that particular conductor given a particular distance. So it's given in milliohms per meter or ohms per kilometer. You'll notice that the resistance is given at two different temperatures. The resistance of copper changes with heat. You'll notice that the resistance actually increases as temperature goes up. So in our table at 25 degrees Celsius, if we were to increase to 105 degrees Celsius, you will see an increase in the resistance of that particular piece of copper. And then also you get a weight. So the weight itself is given in grams per meter or kilograms per kilometer. So if you needed to, carry a bunch of wire up a ladder, you want to know how much it actually weighed. But more practical purposes, if you had to string wire between two telephone poles, you needed to know the actual force on those poles that the wire is causing. So how much weight is actually being applied on those telephone poles or hydro poles from the wire itself. So copper conductors have a certain amount of weight to them. A perfect example of all of this, if we take American wire gauge 14. So if we looked at American wire gauge 14, so if you scroll down the left-hand column to gauge number 14, you can see that the diameter is 1.63 millimeters. You can see the cross-sectional area is 2.08 millimeters squared. You'll see that the resistance is 8.43 milliohms per meter at 25 degrees Celsius and 11 milliohms per meter at 105 degrees Celsius. You can also see that it's 18.5 kilograms for a kilometer of that wire. American wire gauge 14 is important because that is the main wire that you have running through your house. So if you were actually looking at the wires that are going through the walls of your house, they're going to be typically 14 gauge wire. So that's a standard throughout your house. Now, why does gauge actually matter? Well, on this next table, there's something called ampacity. So again, along the left-hand side, you'll see a bunch of gauges. And then the rest of that chart shows ampacity based on the type of, is it copper or aluminum, and also the type of insulation. So what is ampacity? Well, ampacity is the maximum safe amount of current that a conductor can handle. Is it the ultimate peak or maximum that a conductor can handle? No. It is the safe rated current. So the bigger the conductor, the more current it can handle without being damaged. So if we looked right at the top of the left-hand column, you'll see that gauge 14 is one of the first gauges that you have there in this particular table. So this table came from the National Electrical Code. So gauge 14 typically has an ampacity of 20 amps. So depending on what type of an insulator, you can actually go from 20 to 25 amps flowing through a 14 gauge copper wire. If we went down the chart to, let's say, a 4 gauge wire, you'll see that that increases to 70 all the way up to 95 amps flowing through that wire. Again, it depends on the insulation. So as current flows through a wire, it warms the wire. That's why the insulation makes a factor and it plays a role in how much current you can actually have inside a conductor. So just in summary for conductors, we have such a thing called as the American wire gauge chart, and what that sets out is the properties of round conductors. So what that tells us again is how big is the actual wire. So the diameter, the area, how much does it weigh, and what is the resistance over the length. So if you remember, hopefully from your early studies, when we're looking at a conductor, the smaller the conductor, the larger the resistance. The larger the conductor, the lower the resistance. And then that all plays a part in ampacity. Ampacity, again, is the safe rated current for a conductor. So a given size conductor with a given insulation, what is the maximum safe amount of current that can actually flow through a conductor? Now what about insulators? Now an insulator, there are some definitions that you need to know. They're up on the screen. There's permittivity. The permittivity of a material is the property of a material which permits the establishment of an electric field. It's a counterpart of permeability in magnetics. So later when we talk about magnetics, magnetics is the ability, or permeability in magnetics is the ability to set up a magnetic field. Permittivity is the ability of a material to set up an electric field. There's a material called, or something called the dielectric, and that in insulating materials, any insulating type material that is exposed to electric fields are called dielectrics. The dielectric strength of a material decides the maximum voltage that can be applied without breakdown to that dielectric. So if you go back to my example with the lightning hitting the tree, how much voltage is required, or how much energy is required to actually conduct through that tree? So there are some examples there: air, oil, paper, Teflon. So if you had 1 millimeter of air, you need 3,000 volts to actually jump that gap. If you had 1 millimeter of Teflon, you need 60,000 volts to burn through that Teflon. So just some examples. The dielectric constant. Dielectric constant is used to compare how insulating materials between metal conductors would affect the capacitance of the equipment. All materials have dielectric constants that are compared to that of a vacuum. So 1, 2, 3, 4 little definitions that you should know. And the reason you need to know those is when you look at the properties of insulating materials, you can see that depending on the insulator, you have electrical properties, you have thermal properties, and you have mechanical properties. The one that we're looking at mostly is the electrical properties. So there is your dielectric strength and dielectric constant. So again, dielectric strength, the strength of a material, decides the maximum voltage that can be applied without breakdown. So depending on what type of insulator you're looking at, you're going to have a different dielectric strength. You do not need to memorize any of these tables. You do need to be able to utilize that information if asked. So next what comes up is, what happens if we exceed the rated current? So when you look at the ampacity of a conductor, so I have American wire gauge 14, it's designed to handle 20 amps of current, but what happens if we exceed the 20 amps of current? Well, if we exceed the 20 amps of current, then that means we're putting more current through that wire than it's designed to handle. That means that the wire will start to overheat. We need to protect against that. So that's what's called overcurrent protection. So if we were to accidentally put 30 amps through a 20 amp circuit, we need to be able to realize that is bad, and we need to be able to stop that from happening. So we have what's known as overcurrent protection devices. The most common one that you're going to come across is a fuse. The symbol for a fuse looks like that. Fuses are given ratings, 5 amps. Sometimes you'll see a symbol that looks like this. That could also resemble a fuse. Here is a fuse. So basically, this fuse is designed to open the circuit when current exceeds 5 amps. There's something called clearing time. The clearing time of a fuse or overcurrent device is the amount of time it actually takes for the fuse to blow if I exceed 5 amps, as my example. So if this was a 5 amp fuse and I put 6 amps through it, how long would it take to blow? That is clearing time. Okay, so how long does it actually take the device to blow once I exceed the current? The higher the current, the shorter the clearing time. So the more I exceed the current rating, the faster the overcurrent device will blow. There are typically two types of fuses. So if we looked at the fuse, they come in many styles, but they come down into two different categories. One is called a fast blow fuse, and the other is called a slow blow fuse. And what it comes down to is clearing time. A fast blow fuse will blow faster than a slow blow fuse given the same current input. The reason we have two different devices is so that if we need immediate protection from excess amount of current, we could put a fast blowing fuse there that'll blow almost instantly, therefore saving the device. Sometimes current will spike momentarily and then fall back down. So we don't want the circuit to blow right away. We want to give it a couple of seconds to recover, or else we could be blowing fuses instantly all day long. An example is a motor circuit. If we actually looked at time versus current of a motor, when I start a motor, so here's my starting time of the motor right here. When I start the motor, the current jumps way up high. But once the motor starts to run, the current actually falls and then levels off. So if I put a fast blow fuse in a motor circuit, every time I turn the motor on, the fuse will blow. So let's pretend if I had my 5 amp example, here we go. Here's 5 amps. So as soon as I turn the motor on, I instantly will get higher than 5 amps. If I put a fast blow fuse in, that'll blow. The normal operation of the motor is to put large amounts of current, but once the motor starts to spin, that current falls. So notice the current, what they call the running current of that motor, is far below 5 amps. So that will not blow. So what we do is we put a slow blow fuse in there so that it allows for this quick little spike, and then when the current dies off in its normal operation, the fuse will maintain its current flow. If somewhere down the line there was a problem and this current spiked up over here for a period of time, then the fuse would blow. So depending on what we want to use the fuse for, do we want to protect something quick? Okay, so if we want to protect something quick, we want a very short clearing time. That's a fast blow. If we want the circuit to be able to recover from quick spikes, we put a slow blow fuse because it takes longer for the fuse to actually blow. So fuses come in many different styles, sizes. They come in physical sizes different. This is a very, very common one that you're going to see in electronics. All right, one of the downsides of fuses is typically when the fuse blows, you have to throw it away and replace it. So we have what's known as circuit breakers. So circuit breakers do the same job as a fuse, only typically they are resettable, so you don't have to throw it out every time it pops. You just basically go in and reset the thing. So a circuit breaker. If you looked at the circuit breakers, or the common circuit breakers you find in a panel, there are three types of circuit breakers. The first one is what's known as thermal. A thermal breaker. Then there is thermal magnetic. And then we have magnetic. So three different types of technologies, if you will, that are used inside circuit breakers. So we have thermal, thermal magnetic, and then purely magnetic. Okay, so the thermal circuit breaker. Basically what we have is a set of contacts. So here's where the circuit is made or broken. So under normal use, we have current that can actually flow up through this, up through the contacts to the load, and return to the power supply. The contacts are spring loaded, so there's a force that's trying to pull this down. But it's sitting on top of this little arm. So this little arm holds the contacts closed. If that arm is moved out of the way, then the spring pulls the contacts open. So here's what happens. This part here that the contacts are resting on is actually made up of two pieces of metal that are laminated together. There are two different types of metal. So what that means is when the metal is heated up, because it's two different types of metal, they have two different coefficients of thermal expansion. So what that means is they expand at different rates as they're heated. So what ends up happening as these two pieces of metal are heated, they start to bend. So as current increases, it will cause the metal to heat up at a predetermined value. So again, let's say this is a 15 amp breaker. So above 15 amps, we're going to be providing enough current here to cause these things to heat up. They heat up and they expand, and therefore they bend. When it bends, it actually pulls itself away from this little arm. The spring can then pull the contacts open. Typically now there's a little reset. So what happens is once the contacts cool, we can actually lift up this arm and put the metal piece underneath, and we're all set back up again. And again, what will happen is as the current increases past the limit, these things will bend, the contacts will be opened by the spring. And then again, once everything cools off, the arm is lifted back, contacts are closed, and this is put back into place. So over and over again, we can use this breaker. So 15 amps, again, if we were looking at protecting a circuit for, we had wires that could handle safely 20 amps. We could put a 15 amp breaker or a 20 amp breaker. And what would happen is, as we exceeded the ampacity of the wire, then this would pop, stopping current from flowing. The thermal magnetic is the same idea. Again, I have current flowing. Let's pretend again we got 15 amps. If we exceed the 15 amps, it would be enough current to cause that metal to heat and start to bend. There's a magnet sitting here, and the magnet has attraction. So therefore, once the pieces of metal start to move ever so slightly from bending, then the magnet takes over and snaps it. So the magnet actually attracts these pieces of metal. So same concept as the thermal, but instead of having to wait for it to bend all the way, it just has to start, and then the magnet takes over. So this type of device has a faster clearing time than this device. So this device, we have to wait for everything to heat up enough to bend the metal. In this case, all we have to do is start bending the metal, and then the magnet snaps it open. So this is a faster clearing time. The last type that you'll come across is magnetic. So this one, there's no thermal properties at all. Basically, and again, let's take a 15 amp breaker as an example. So here's our contacts. The contacts again are spring loaded, and they're sitting on top of this. So this is basically like a bent piece of metal that has a pivot point. So just as an example, I will take this piece of wire that is almost that size and put it there. So we now have current, and the current will flow up, and it flows through a coil. This is an electromagnet. Once the current builds up enough and exceeds this 15 amps, the magnetic field that is created will be strong enough to attract that arm. So what happens is the arm gets attracted to the magnet, pulls out from underneath the contacts, the spring then opens up the contacts, breaking the circuit. Then we basically click a button, and this basically goes back up underneath, and we're all set to use again. So this one is using an electromagnet. So again, once the current is strong enough, it will create a magnetic field that is strong enough to pull this arm. And once it does, it pulls it from out underneath the contact, and the spring will do its job. So, three types of resettable circuit breakers: thermal, thermal magnetic, and purely magnetic. What are some advantages and disadvantages? Thermal is the cheapest. So cheapest to manufacture, cheapest to buy. The Magnetic is the most expensive. This is slow. This is faster. This is fastest. This one is affected by temperature. So remember, it's all thermal. So if you were operating this in a situation that was, oh, I don't know, 70 degrees Celsius, 80 degrees Celsius, that ambient temperature will already have an effect on this metal. So this one here, as well as this one here, are affected by heat, where this one is not. Now, on the other side, these two are not affected by any electromagnetic interference. Depending on the placement of this, we could have electromagnetic interference that interferes with creating this magnetic field. Could prematurely cause it to trip, or cause it not to trip at all. So each has its advantages and each with its disadvantage. So the most common one you're going to find in your house is the thermal. Why? Because it's the cheapest, easy to operate. That's typically what you find in the circuit breakers of your home. So for today, we looked at conductors, insulators, overcurrent protection devices. So we looked at the properties of conductors, American wire gauge ampacity, and we also looked at insulators. So we looked at things like dielectric and dielectric strength, and then overcurrent protection devices such as fuses and thermal and thermomagnetic and magnetic breakers. Now, thermal, magnetic, and just plain old thermal will not save your life. The job of these, to save the life of the equipment that's connected to it. So the wires, the actual equipment, all that kind of stuff from overcurrent. If you are waiting for one of these things to pop and save your life, 15 amps of current is an awful lot of current to go through your body for a couple of minutes while you're waiting for these things to pop. You will not survive. These are not designed to save you. They are designed to save the equipment from overcurrent. So, I hope that helps. Until next time, everybody stay safe. Take care.